here. Right, so let's start with any questions that you might have. Remember, when you do say, just say which year or booklet number would be great. Booklet 1, 2, 3. That you have any questions on. I'm just going to get that is number 1, that's number 2, and that is number 3. So everybody did something to do with quantitative chemistry in their last lesson. Oh, and there's questions already. 2A1, 2A2, 2A3, 3, all the question 8. Yeah, 7. Sure, that's presumably booklet 1, but I'm assuming that is the one you're talking about. Calculate the mass of chlorine. Yes, I can absolutely help you with that question. No problem. Let me just open up a few things in front of me so I can see them. I'm going to end up doing all of the questions today, I reckon. Mhm. Right, I'll get through the question that people have asked me so far. I'll do. Yeah, I got you. I got it. Yeah. So I'll do the one from booklet 2 first, just because there's one question from there, which might be repeated, because some of the question will be repeated. Um, so there was a question here in which you had to. I want to do all of question 2 here. This might repeat in another booklet, just so you know. Um, Swimming pools are treated in order to kill microbes. One type of treatment is adding something called calcium hypochlorite tablets. It gives you the formula CaCl2O2. Calculate the relative formula mass. So you should have done lots of this in the lesson, which was basically adding up loads of numbers. So this is a compound which is made up of lots of different atoms, and we're trying to work out the total mass of this atom, of this compound now, by adding up the individual atoms. So we have a calcium, which is worth 40. We have 2 chlorines, which is 2 times the mass of 1 chlorine, plus 2 oxygens, so 2 times the mass of an oxygen, which is, if I get my calculator out, 143 should be the answer to that question. Then it says calculate the percentage by mass of chlorine. Out of all of this, 143, this much came from chlorine, 2 times 35.5. So that's 71. That's what 2 times 35.5 is. 71 out of the 143 came from chlorine. You times that by 100. That is just over 50%, isn't it? Just under. 49.65%. Okay, I mean, you can call it 50%. I don't think it matters too much. Let's see what the mark scheme says. Yeah, 49.7%. If you did 50%, it's really okay. Okay, then this is the question that you've actually asked, which is calculate the mass of chlorine in a 20-gram tablet of calcium hypochlorite. What this is saying here, what you have just worked out here, is that if you had a load of this tablet, then 49.7% of it is chlorine. That's what it's just worked out. You worked out that 49.7% of this whole thing is chlorine. Now, what we're saying is that one of these actually weighs 20 grams. So this percentage still applies. So when it says calculate the mass of chlorine in a 20-gram tablet, what you're doing is working out this percentage of the tablet, and the tablet now is 20 grams. So you're working out 49.7% of 20 grams, which you could do like this. 49.7% means out of 100 times 20. So it's going to be about 10, isn't it? Because it's roughly 50%. 9.94. That would be the answer. So really, what you did in part B or A part 2 is worked out in any of these tablets or any of this amount, how much is chlorine? 49.7%. Now we're saying this is how much we've got. So it is 49.7% of this much. Why would it be 49.7% and not 49%? Um, for part A, part two, because the question is calculate the percentage by mass of chlorine, and by timesing it by 100, I have turned it into a percentage. That's the answer to that question. Okay, at which point I could move on to the previous booklet, which I think is very similar to this one. I've got a feeling it might be identical. I've got a strange feeling that these are all very, very similar. So, question did all the question two, right? Yeah, two, and all the question two. Three and all of question eight. All of question. I'm not doing all of question three. Absolutely no chance. Um, so for all of these, you need to use the periodic table to find the relative formula mass of the compounds. So let me open up a periodic table to tell you what to do for the first couple, and then you can do all the rest yourself. Um, so some of these got quite long, and I appreciate that there's quite a lot of work to do here, especially if you got told to do the entire booklet. The second part of question three, sorry. Um, I don't know what question three is. Um, is the numbering really off in this? Yeah, I'm not sure what you mean by the second part of question three, if you tell me exactly. The 8 to 12 part. Oh, this part. Right, got it. Okay, fine. Well, again, it's it's a lot of work, this, which is why for some people that I taught, I told them not to do this part. But I'll tell you how you do it. It's very easy. It's just a bit long. Um, so, what is the percentage composition by mass for each element in hydrogen peroxide? Right, what you do first with all of these questions, 8 to 12, let's do 8 first, is work out the relative formula mass of this compound. Now, that is Na3, so 3 Na, so you'd have to look at the periodic table, find Na, and look at the top number. So what I'll just do, just because it'll be easier than scrolling up, is open up a periodic table. It's quite lengthy, this, but it's good practice, which is why it is important to do it. Um, so Na on the periodic table has a 23 on the top. You see that there? 23. So you do 23, there's three of them, times three, plus P, you have to go find P on the periodic table, which is there, 31, plus oxygen, which I know is 16, and there's four of them, 4 times 16. So 23 times 3 plus 31 plus 4 times 16. Right. The relative formula mass of this is 164. Right. Then the question says, what is the percentage by mass for each element in here? Right. What are the elements? There's sodium, Na, there's P, and there's O. So for each of these, you have to do this calculation. This is why this is long, but not difficult. Okay. So what you now have to do is say, okay, out of 164, how much was sodium? Na was 23 times 3, right? So 69 out of 164. You do that fraction times 100 on your calculator, and you will have the answer. So 69 out of 164 times 100, which is 42.1%. Then you do the same thing with the P. How much of that 164 came from the P? That was just this 31. So it's 31 out of 164 times 100. Then you do the same thing with the oxygen. How much of this came from oxygen? That was 4 times 16, which is 64 out of the total. That's why you needed the total in all of these questions, times 100. So that's the calculation you do for all of those. Then you have to do the same thing for this. I'll do it for this one as well, just to show you. In fact, I'll just finish this one off. So 31 out of 164 times 100 is 18.9%. So that will be 18.9%. And then the last one, which you could do in a quicker way, which I'll tell you in a moment, 64 over 164 times 100 is 39%. And the quicker way to do that last part, once you've done everything else, is to remember that percentages add up to 100. So once you had done the first two, you could have 100 takeaway, 42.1 takeaway, 18.9, which would still have given you 39. So with all of these questions, once you don't actually do the very last one, you don't have to do. You just do 100 minus everything else. But for this one, we need the relative formula mass of H2O2. H on the periodic table has a 1 on it, and there's two of them, so 1 times 2. And oxygen has a 16 on it, so there's two lots of 16. That is 32 plus 2, which is 34. So now, the percentage of each element. So we've got H and O. For the H, out of the 34, 2 came from hydrogen times 100. And out of the 34, 32 came from oxygen times 100. So they are your calculations that you do for 8 and 9, and which means that I'm presuming you can do the other ones. It's not that long, is it? I mean, actually, it's shorter than I realized. So you do the same thing for carbon dioxide. I can tell you, for example, that CO2 is 12 for carbon and two lots of 16 for oxygen, which makes 44, which means your calculation for carbon will be 12 out of 44 times 100. Your calculation for oxygen will be 32 out of 44 times 100. You're just working out of this how much came from each element when you did the calculation. You can even do this one actually. Let's do this. That's obviously just 12 plus 16, which is 28. So for carbon, it will be 12 out of 28 times 100. And for oxygen, it will be 16 out of 28 times 100. And I suspect you can do those yourself if you follow the same procedure. And then, was there anything else? Question 8. Okay, I'll just do question 8. Again, I think a lot of this is similar for most people. So probably doing most of the homework. And I suspect we might get through this quite fast as a result of this. Right, you might not have got to this, but it's okay. I'll tell you how to do this. When you do a chemical experiment, you are able to calculate how much you expect to get when you do the reaction. Question 7, I will come to, well, yeah, I'm doing it now basically because it's kind of part of the same explanation. When you do any chemical calculation, you can predict or guess, not guess, but scientifically guess how much you're going to make. Now, when you actually do the experiment, you tend to not make as much as what you expected to make from a calculation, for various reasons, which I won't go into. But you can then work out something called percentage yield. And it's actually just like, I mean, if I said to you that you got 22 out of 30 in a test, and I said turn it into a percentage, you would times it by 100. In the same way, in these kind of questions, they tell you how much they thought they would make, 13.6, and how much they actually made, which is 8.4. And you just do that times 100. That is percentage yield. It is really, really easy. And that is actually the same as what you do in question 7, part A. They expected to make 800, or that's the most they thought they would make. They actually only made 500. So you do 500 out of 800 and turn it into a percentage by timesing it by 100. That's what you do in those questions. A possible reason why the yield was not 100% is usually to do with you can often say errors with the measurement, but let me just check what I wrote when I did this. Yeah, you can just say errors in measuring. Maybe when you mixed your ingredients, so to speak, together, you didn't quite measure them accurately, and so therefore, when you actually did it, you didn't get what you were expecting to get. Okay, and then did that, and then this. I'll do this because of the brackets makes this a little bit weirder. Calculate the relative formula mass of lead nitrate. So I think I know the answer. I think the answer is 207. Let's see if it. Oh no, it's not. Forget that. Sorry, that's just lead. Right. So we've got a lead, which is Pb, which is 207, to which we're adding. Right. When you have brackets, you have to be a little bit careful because you need to work out everything in the bracket first and then times it by 2. So that's what the 2 outside the bracket means. Everything in the bracket gets times by 2. It's a bit like BIDMAS. So you're going to do 2 times everything in the bracket. In the bracket, we've got an N, which is 14, plus 3 oxygens, which is 3 lots of 16. So we've got 207 plus 2 times Do the brackets first. 14 plus 3 times 16 is 62. 207 plus 2 times 62 is 331. That would be the relative formula mass of that one. So you have to be careful with the brackets. Slightly surprised nobody's asked me the last one. Oh, is this still question? Is this why? Because it's all still question 8. Yeah, fine. Okay. Right. This is again, I wouldn't expect you to know. This is quite difficult, this one. We were just thrown in at the end. But if you actually follow what it says, it is not that difficult. So even if you don't have a clue what this means, okay, you can work this out by just reading the question carefully. It says, calculate the percentage atom economy for making zinc sulfate in method 1. Right. So we're ignoring this. We're just looking at this. Okay. It tells you exactly how to do it. That's why we left this in the homework, actually, because if you follow what this says, you should be able to do it. It says, make a fraction, and on the top, put the relative formula mass of zinc sulfate, ZnSO4. Now, it actually tells you that number in the question. So we just put 161 on the top. You don't even have to do the individual adding and stuff for this because it tells you everything. And then it says on the bottom, put the relative formula mass of zinc oxide, ZnO, which is there, plus the relative formula mass of H2SO4, which is there. So they've told you all these numbers. It's a bit like a substitution question. You're just substituting numbers into the right places in the formula. And then it says times 100. And so you just need to type that carefully into your calculator. And it gets you 89.9%. What is a percentage atom economy? How do we figure it out? But by doing exactly what I just did. Because that's how, there's a formula for it. We just followed the formula. That is how you do it. You read the formula and you do what the formula tells you to do. Just so you understand what we've actually done there, in any chemical reaction, ultimately there is one thing we're trying to make. That is what I would call the desired product. There is something else that's often a waste. In this case, water is the wasted thing. We're trying to make zinc sulfate. And so what you do is you take the thing that you want to make, work out its relative formula mass. That's what we just did there. That's where the 161 came from. Then divide it by the total relative formula mass of everything on the left-hand side of the arrow. So you add together zinc oxide, which was 81 there, to H2SO4, which is that number, divide them and times the answer by 100. That is what it is without me explaining how do we arrange the compounds in the equation. So yeah, like that. So on the top, you put the desired product. So because in this question, it actually tells you what we're trying to make. We're trying to make zinc sulfate. We're not trying to make water. That just happens to be a wasted product. So the thing we're trying to make goes on the top. And then the sum of everything on the left-hand side, so the other side of the arrow, goes on the bottom. That's how you rearrange it. Can you do the question 8, part C? Is that this next one? Okay. Right. I'm just going to tell you the answer here. Atom economy is, again, I wouldn't expect everybody to know this, but the idea of atom economy is to do with how much you're wasting or how little you're wasting. This number is very high, 89.9%. That means that when I'm doing this reaction, there is very little wasted. It's like 10% is wasted, and then 90% is useful to me. It is something that I wanted to make. And so it tells you method 1 gives a higher percentage atom economy than method 2. So method 1 is better in the sense that it gives a bigger percentage. Why is that important? It basically means that there's less waste. Because ultimately, that's what atom economy is doing. It's working out what percentage turns out to be useful to me. We don't really want a chemical reaction that is 10% useful, because that's a big waste, 90% wasted. But if it's 90% useful, only 10% wasted, then that's better. So both of these reactions, just so you know, I'll just show you this. Both of these reactions involve making zinc sulfate. You see that? There's two different ways of making it, though. One is method one is method two. Method one is slightly better, and essentially, to keep it very simple, it's because this is the only thing wasted in method one, but in method two, we get more stuff wasted. Got my rainbow pen. Um, so that's it. There's more stuff wasted here, so that makes method one slightly better than method two. That's what atom economy is measuring. It is about wastage or usefulness from a reaction. Have I just done the whole booklet? I basically have, haven't I? Done that, done that, done that, done most of those. I don't think anybody needs help with these really. It's just adding up some numbers. Um, did that one. And you know what? May as well just do question one just to finish off. Right. So, calculate the relative formula mass of ammonium nitrate. So quite a big compound here. You have to just be careful when you're adding up stuff. So we have an N, which is 14, plus four H's, and each H is 1. So 4 times 1, plus another N, which is 14, plus three oxygens, 3 times 16. And if you type all that into the calculator, then you will get 80 as the answer. As I mentioned to some of the students that I taught, sometimes, especially if in your year seven, year eight kind of thing, you are sort of accustomed to try and do things in your head, like work out 14 plus 4 times 1, then add another 14, then add 3 times 6, like trying to do it all in your head. When you do science, remember, you will always have a calculator, so don't try and make things harder for yourself. In maths, obviously, you have to be able to do things without a calculator, but this isn't maths. So write down the calculation, then use a calculator to work it out. We just want to get to the right answer, not testing your mental arithmetic. Potassium nitrate is a fertilizer spelt wrong with the formula KNO3. The relative formula mass of potassium nitrate is 101. Calculate the percentage by mass of potassium in potassium nitrate. So they have already done the adding up at the beginning. They've said it all adds up to 101. But now we want to know what percentage of that 101 comes from potassium. Potassium, by the way, is K. So how much of that came from K? Well, K is worth 39, and there's only one of them. So it's 39 out of 101. That's the fraction of potassium in this compound. Turn into a percentage by timesing it by 100. I accidentally went on to the English on Monday, waited for hours, Wednesday, sorry, I came on here. Oop, okay, fine. Yeah, I'm going to try and combine this next time and so that we can get both everything on the same link. It's just difficult with recording stuff. That's why we have two separate links, Monday and Wednesday. Right, that's the answer to that. Then, this is a good, slightly harder question, so I want to do this. Slightly surprised nobody asked me this. We have a metal oxide which has a formula XO, but X is not the symbol for the metal. So it's something O, right? So let's just put a box here. There's something O. It tells you the relative atomic mass of oxygen is 16. And so we know it's 16, right? And then we know the relative formula mass, in other words, everything added together makes 81. So there's some number up here. When we add it to 16, we get 81. So we should be able to work out what that missing number is by doing 81 take away 16. It's a bit like a algebraic equation. And we get 65. So that missing thing must be worth 65, so that when we add it to 16, it makes 81. And then it says, use your answer on the periodic table to name metal X. So what we need to do is find the element which has a mass number of 65. So on this periodic table, those numbers are at the top. You find 65, and it is zinc. More questions. Will there be a lesson this week or next week? I don't know what that means. Oh, yes, there will. Sorry, your normal lessons are as normal. Yeah, so unless you attend your normal lesson on a Thursday, which is when there are a couple of bank holidays, Christmas Day and New Year's Day, your lessons are as normal completely. There are no changes to any lessons during the holidays, just so you know. Sadly. Right, scroll up to question 7. Is that everybody done? Right. As far as you guys are concerned in key stage three, which is the most of the people that are here, the thing, if you can just be confident with um, doing basically this stuff here, which I appreciate is the longer bit. But if you can do that, then at this stage you're pretty good. So working out relative formula math, which is adding up some numbers, and then doing the percentage bit from there, depending on the question. Um, um, I'm not telling you the answer to question seven. I think you can work that out yourself. But that is the working out for it. So yes, just so you know, again, for all of you, as you do more complicated chemistry, you will be learning about, and you may have done some of this anyway, about the mole, which there wasn't anything on that in the homework, but the mole is a way of measuring the number of particles in a chemical, which is what we need to do when we do any calculations. We don't use grams because that doesn't really tell us anything. It just tells me how heavy something is. But what I really want to know when I do a calculation is how many of these little things there are inside my beaker, right? Not how much it weighs because they weigh different particles weigh different amounts. So that is the next stage. And if you want to stick around for 8 till 9, I don't know why you would, but if you wanted to, then I'll be doing some more complicated calculations involving these things. But for now, it is a good point at which to do that. Does anybody have any other questions with regards to any of the key stage three stuff? I guess you don't because I've answered the whole thing. Um, I won't go yet because it's too early to let you go. Um, Next week, you know what I'll do? I'll introduce you to next week because I've just been doing it because some people have their lesson today. Next week, everybody of you guys anyway, are doing a physics topic called waves. And what I'll just do is tell you something. Oh, there's more. There's more. Can I go through that? By that, what does that mean? Waves. Is that what you're talking about? Waves. So let me tell you, actually, that's a good point. You know what? I won't go to waves. The booklet you were on now at the Key X3. Yeah, I've just been through the whole booklet, I think. I think everybody had the same one, didn't they? Did they? No, they didn't. Um, you need to tell me some questions. I'm not going to go through it. I need question numbers. Um, So nobody had asked me anything from booklet three, which is why I haven't done anything on booklet three. But if you have any specific questions, I can try to answer some of them. I won't do lots of them at this time. They need to come at the beginning. But if you have a couple, I can help you with them. But meanwhile, let me just explain one of the things of quantitative chemistry, which you might not have covered off in the lesson. If I gave you the following equation, magnesium plus oxygen gives magnesium oxide. And I balance this equation. It balances to the following. Okay. But then, if I asked you this question, which is, if I combine or if I react 6 grams of magnesium with 4 grams of oxygen, how much of this do I make? If I asked you that question, I suspect everybody would get the correct answer. Um, and surely that correct answer is 10. Right? Like if I told you that much information, you'd hopefully correctly say it's going to be 10 grams. Yes, of course. If I do react 6 grams of this with 4 grams of this, then the answer I get is 10 grams. However, if I had not told you this and asked you the same question, if I said I'm going to start with 6 grams of magnesium, how much of this will I make? Suddenly, that is a much more complicated question. How do you answer that question without knowing how much of this is going to react with it? But we can work it out. And that's basically what quantitative chemistry is to an extent. You essentially work out how many particles of magnesium you've got And then you basically can figure out how many of these will react with it. And then you can figure out how much this has gone away. It is essentially that, without going into too much detail. That is what quantitative chemistry is about. It's like, if I start with this much of this, how much of this will I end up making, without giving you any more information. So that's what quantitative chemistry does. And it requires this thing called the mole, which is a unit of measurement that basically tells you how many of these little particles there are. And then you can figure out how many of oxygen particles will react with it, because this kind of tells you. Um, and then you can figure out how much of this you're going to make. So it's a bit of a complicated thing without going too much into it. Right, I will just open up the third booklet because there is time. Is there anybody who has any specific questions from the third booklet, which is different to the other two? It's more complicated because it has other topics involved with it other than just calculations. I should open it up, shouldn't I? Three, please. From booklet three, I assume that is what you're talking about. Yeah. Um, this one. This one. Is that what you want? Three. Um, okay. So if that is the question that you're asking me, okay, then it says calculate the relative formula mass of CaO. Right, that is a compound that contains one calcium and one oxygen. The mass of calcium is given to you there as 40, and the mass of oxygen is given to you there, which is 16. You add them together and you get 56. That would be the first part of that. The next part of that is slightly more awkward because of the brackets. So we have got effectively one calcium here, which is worth 40. Then what this 2 means is that there's two oxygens and two hydrogens. That's what the brackets do. It basically, you know, applies the number outside it to everything inside it. So there's two oxygens and two hydrogens, and each hydrogen is worth one. So that is 40 plus 32, which is 72, plus 2, which is 74. That's the answer. And then most of these, a lot of these are very similar in terms of those questions. Um, the one question that will be not really possible, I suspect, is question number 10, as and when you get to it. Yeah, because yeah, that wouldn't work. Um, that's sort of just fallen into this slightly by accident. Um, but let me see if I can do this. Okay, I will do this. For those of you that are here for the next session, this is helpful for you. But the question said, if I start with 2 grams of hydrogen, how much of this hydrogen chloride do I make? Okay, again, I wouldn't necessarily expect you to be able to do this, but I shall tell you. What you have to do is convert this to moles. To convert grams to moles, you take the mass in grams and divide by the relative formula mass of hydrogen, or H2, which is 2, which means that is 1 mole. Then what you do is you look at this balanced equation and notice that if one of these makes two of these, then I've actually got 2 moles of hydrogen chloride here. And then I've got to convert that back to grams by timesing it by the MR of HCl. HCl is 1 plus 35.5, which is 36.5. 2 times 36.5 gives me 73 grams. I would not expect you to know that, just so you know, for those of you who are doing that one. But that is what you do. Anything else that stands out here? This is really easy because this is like that question I just showed you with the 6 plus 4. So it says I made 100 grams of, well, I started with 100 grams of this. What did I make here if I made 44 there? Surely it is just 56 because it just adds up to 100 over here. Um, and then this is the same question, just it's 56 again. That should be easy enough. Um, Often people get stuck with this question, which is that what does it mean by an instrumental method? It's like saying, just so you know for future reference, if you get this kind of question, if I said to you, or if you said to me, what is the temperature, or what's it like outside, or what's the temperature like outside, and I said it's quite cold, then that is a not an instrumental method. I have not used any sort of instrument to give me any sort of proper indication of what the temperature is like. I've just said very cold. I'm not wrong. I'm not wrong, am I? It is cold. But an instrumental method means that I would maybe use a thermometer and get an actual number and give you a more accurate, more precise answer. And that applies to any situation. If you want to use an instrumental method, means you are using some piece of apparatus to measure temperature or volume or mass, rather than just winging it and going, well, it's roughly this much. That's essentially what an instrumental method does. It's fairly obvious when you explain it like that. Um, right. I think that's it. There's no more questions on this. Right. I think, given that there's no more, I will stop there and then I will return at 8 p.m. to do some of the more complicated quantitative chemistry that was given. To the others, I don't think it's much more complicated, actually. Oh, yeah, it is. Okay, fine. We will talk about this afterwards. Um, Statistics and math, I don't know. We probably won't have time for it today, but I can sort of deal with it if you want it separately during the holidays at some point. I could probably find some time for it. But yes, I will be back shortly. Right, hello. Um, 3D, someone has asked, which booklet are we referring to and which one? But anybody else got any other um, questions from quantitative chemistry? I will end up doing quite a few questions from these two booklets that people had over the course of the last lesson. Um, Year 10, question 3D. Let's have a look. Right. In this question, we had to do some calculation, which should have been hopefully easy enough. Tell me if not. And then it said an unwanted side effect of this medicine is that it can cause the patient to have wind. The equation below represents the reaction between calcium carbonate and hydrochloric acid, which is the acid present in the stomach. Suggest why they may suffer from wind. The answer is there. When this stuff goes into your stomach, then one of the products is carbon dioxide gas, which is what causes the wind. And that is the answer to that question. 6BI, is that also from the same booklet? I'm going to assume it is. Um, okay, right. Oh, I know this is the same question as the last booklet. Right, so there is some metal oxide, something O. We don't know what the something is. It is not M. Um, and they've told you that to calculate the relative atomic mass of metal M, so we've got something, which is whatever M is, plus the O, which is 16, and that gives you a relative formula mass of 81, which means that the missing number here is 81 take away 16, which is 65. And then what you have to do is go to the periodic table and find the element which has a mass number of 65, which you will do and find it there. It is zinc. I may be able to go back to the year seven booklet, but I'm not going to prioritize that at the moment, because I have done the whole booklet, I think, literally the whole thing, earlier. And as I say, there is a recording of this, so you are able to watch it, back later. But I did do all of those earlier. But I will first prioritize anybody who's got anything from this one, because there are some more complicated things that I need to go through. Okay, let me also open up a few things. The recording is all ends up on our YouTube page. There will be in the email that I send every week, there is a link to the YouTube page. You'll be able to find it if you go to the live section. So about an hour or so after this ends, it ends up there automatically. And you'll find all of them there actually, going back a while. But if you're unsure, then just send us a message and I will point you in the right direction once it's up. Yep, again, the booklet three, I'm not going to do now because of the fact that I did most of these in the last session, but let me see if I can do it now. I'm just, um, 6B part one, is that just, be clear if it's your year 10 or year 11, because I think they had slightly different booklets. Um, Year 10, yep, all right, okay. 1E has been asked. I mean, I don't, that it's just adding up. Okay, right. I'll see if I can come back to that later. And question three. I've done question three there. Okay. So 6B part one and B part two. Let's have a look. Okay, done that one. Sorry. Oh, 6B part two, done that. Uh, year 10, question eight, and then seven and two at the back. Right, this one. Yeah, that's the kind of question I want to do. And then 7 and 2 at the back. Yeah, fine. 7 and 12. Is it 12 at the back? Okay, anyway, I'll do most of these. 12, yep, got it. All right, question 8. A very common question that you will get in GCSE chemistry is explaining why a metal conducts electricity. A very common question. So they may mention copper, they may mention something else. In this case, it is mentioned copper. The answer is always the same. It is that any metal has something called delocalized electrons. So that means that within the structure of it, delocalized means free. So there's these electrons that can move around. And what is conduction of electricity? It basically means that we get electricity at one side and are able to move it through the structure from one side to another. That's what wires do. And so the fact that they're free means that they are able to move through the structure. Oops. And carry the charge. So that's what we're supposed to do there. Yes, it's a part of metallic bonding. So there is a section of the syllabus. We did it when we did bonding in the second chemistry lesson, year 10s, where we did ionic bonding and covalent bonding, and there will have been a small section related to metallic bonding, which is basically what metals are like. So all metals, not just copper, have these things called delocalized electrons, which is what allows them to conduct electricity. So yes, when you say you're just supposed to know it, yes, as in it is taught. So yes. Right, this question is the kind of question that I really want to focus on because it is the proper calculations when it comes to this stuff. So iron chloride can be produced by this reaction. There it is, iron chloride. Calculate the maximum mass of iron chloride that can be produced from 11.2 grams of iron. There's the iron. So what I always do when I do these questions is I pick out from the equation the bits that are relevant. So the question is, from some of this, how much of this do I make? So we're not really bothered about the chlorine in this particular instance. So we don't need to write it down. Then what I'm going to do below this is write down the mass of the iron. So 11.2 grams. That's what the question tells me. And what we're trying to work out is how much of this we will make when we do this question or when we do this reaction. The whole point of this is that we cannot work with grams when we do these questions. We have to convert the grams to something called moles, which are a unit of measurement that tell you effectively the number of particles that are in that chemical or that amount of that chemical. So there is a formula, which is that moles equals the mass in grams divided by the MR, or the relative formula mass of that chemical. So to turn this into moles, I will divide 11.2 by the mass number of iron, which is 56. And that tells me that I've got 0.2 moles. Okay, the whole benefit of converting to moles is that you can now look at the balanced equation. That's the really important thing to realize how useful a balanced equation is when we have moles, because it tells you a ratio. It tells you that if you had 2 moles of iron, you would have exactly the same number of moles of iron chloride, because it's a 2 to 2, it's the same number. Okay. And so that means that if I've got 0.2 moles of iron, then I'm also going to make the same number of moles of iron chloride. That's the usefulness of this balanced equation. It's only useful once you've got moles to work with, and you can get to moles very easily, as I just did. Then we're nearly finished because we don't want the answer in moles, we want the answer in grams. So now what we need to do is change this back to grams, which you can do by using this equation again, because if I want to get to grams, I can do moles times the MR. The MR of this compound now, iron chloride, is the iron, which is 56, plus three chlorines, and each chlorine is 35.5, and that is 162.5. So if I timed this by 162.5, I will turn this back into grams, and it will become 32.5 grams. Whoa. That is the answer to this question. So generally, when you do these questions, you'll find if you do this as the way I did it, you will always kind of work your way down one side to convert it to moles, then be able to work out the moles of something else, and then turn those back into grams. So you kind of follow this sort of down and up motion. If you do the calc, if we do another one of these, you'll see me do the same thing again. Let's see what the questions are saying. Do we just find MR to find moles, then do the ratio? Find MR to find moles. Yes. Yes. Do we just find MR to find moles and do the ratio? Why is the answer not 162.5? Because 162.5 is the effectively the mass of 1 mole of iron chloride. But we don't have 1 mole. We've only got 0.2 moles. So that's why it's a fraction of that number. It's not the number itself. Yeah, I mean, your way will ultimately be the same as my way. You just done it in a different order, probably. So yes. 6B part one and 6B part two. Didn't I do that? I'm sure I've already done that. Yeah, did that. Unless it's on the year 11 one you're talking about, you have to tell me. 1E, year 10. You've asked how can I revise chemistry? It's too vague a question. Um, Best thing to do is identify topics that you need to revise and then ask us for questions or watch the videos, which nobody seems to do, but you have access to a lot of content. It is up to you whether you want to use it or not. If we multiplied 0.2, that was A, not B. Okay. Hang on, let me get back to that first. Oh yeah, B. Sorry, yeah, that's a good point. I'll come to that now. But if we multiplied 0.2 by 2 at the start, will we not have to multiply it later on by 100? God. I'll come to that in a second. Let me think about that. Let me think about what you're saying. If we multiplied 0.2 by 2 at the start, not. Yeah, I don't. I don't see how that gets you to the answer of 32.5. If we multiply 0.2 by 2 at the start, that's here. Will we not have to multiply it later on by 162.5 then? Well, one, I'm not sure what that means, firstly, but once you've got to the number of moles here, then you look at this and this. Because they're the same, these will be the same. This is a ratio, it's a 2 to 2 ratio, right? If I've got a 2 to 2 ratio, then 0.2 is also to 0.2, the same number. That allowed me to get to the number of moles here. Now I need to convert moles back to grams, and you convert moles back to grams by timesing by the MR, in this case 162.5. Let me do that 6B. I'll do another one of these, then it might make more sense. Um, Explain in terms of electron how an iron atom can change into an iron oxide ion. Well, okay. This is to do with ionic bonding. If I've got an atom and it's now become a positively charged ion, the only way an atom becomes positively charged is by losing some electrons, because the electrons are the negatively charged things. So if you lose something that's negatively charged, overall what's left behind is positively charged. And specifically, if it's become 3 plus, we must have lost 3 electrons. That is how an iron atom changed into an Fe3 plus by losing 3 electrons. Let me see if there's any other calculation question here that I can do. Percentage yield should be easy enough. All right, there was a question at the end as well that I need to do. Okay, I'll just do these because I've been asked. A student is making perfume using violet flowers. They did an experiment to extract the perfume from the flowers using the apparatus shown below. What is the name of the apparatus labeled X? It's called a condenser. It's what you use when you evaporate something and then you change it back. Changing it back is condensing. So that's what that is. Name the process shown in figure 21.1. Is this not distillation? Yes, it is. Distillation is the process when, for example, if I said to you, I've got some water with salt inside and I wanted to remove or separate the salt in the water, we would do something called distillation. Heat this up, the water would evaporate, and then you'll condense it down here. That's called distillation. 2 changes you could make to set the apparatus. I don't know what you've done wrong. What have you done wrong here? Uh, look. Um, okay. I mean, this is ridiculous, this question. One answer says you need a thermometer because if you are heating this up, you need to know what temperature to do it till. So you could add a thermometer. I'm not sure how you would guess that really. And the other one is I'm trying to see which one I should tell you. Okay, the other mark for this, which doesn't quite make sense, is that the water needs to come out at the top of the condenser. So like there. Not sure how you would know that really. Yeah, water should come out at the top of the condenser. That's what it says. But don't worry about it too much. Let's focus on the calculation here. Student finds out that phosphate fertilizer used to help to grow flowers. Compound A is a fertilizer of M with a formula M3PO4. Okay, it tells you the relative formula mass of the compound A is 164. So if you added up all of these things, remember M is not the actual symbol for this. But what we can do is work out the relative formula mass or the relative atomic mass of whatever M is, because we know that we don't know what this number is, right? But we do know that 3 times that number plus P, which I need to use the periodic table to find, P is 31 plus 4 oxygens, that's 4 times 16, equals 164. That is how you would work out the relative formula mass of that compound. We just don't know what this number is. But we do know that in total it adds up to 164 because it tells you. And so now what I can do is do a bit of algebra and work this out. So 3 times whatever that number is plus 31 plus 4 times 16 is 95 equals 164. If we take away 95, then 3 times some number equals 69. And to work out this number, you divide this by 3 and you would get 23 as the atomic mass of whatever that element is. And now I can go to the periodic table, find the number 23, and I'll find it there. And it is sodium. Okay. We are for year 11, we are continuing with we're doing electromagnetism again, but going into the bits that we wouldn't have got to last time. We do electromagnetism more than once because it is quite complicated, and then hopefully we'll be going into things like alternators and dynamos, and stuff with year 11, which we might not have got to last time, and transformers. It gets a little bit more complicated than what you might have done last time. Right. Um, question 12. Question 12. Yeah, 10. I'm on it. Right. In another stage, the pure titanium chloride, TiCl4, it's not written very well. It should be TiCl4, like that, is reacted with 500 moles of magnesium and excess. Calculate firstly the number of moles in 45,000 grams of titanium chloride. Okay, so remember to calculate moles, you do the mass in grams divided by mR. The mass in grams is 45,000. I'll divide that by the mR of titanium chloride, which is 48 plus 4 chlorines, which is 4 lots of 35.5, which gives me 190. That is the mR of titanium chloride. And so to turn that into moles, it is 236.8, based on my quick calculation. Right. And then show, this is a bit harder, this question, show that the 500 moles of magnesium added is an excess. Okay. Again, one thing that I will try and stress to you at this point is the importance of understanding how important the balanced equation is in chemistry. Sometimes we gloss over it and kind of go, as well, it's done, it's just the equation. We don't look at it properly. But you need to understand how important this is when it comes to calculations. Because what this is telling you is, there's no number in front of this, but there's a 1 there. What it's telling you is that there is a 1 to 2 ratio in terms of the moles of what will react together here. So we're saying that if I've got 1 mole of titanium chloride, it will react with 2 moles of magnesium. That's what will happen. And when it's done that, we run out of stuff to react with. It's all to do with the number of particles. Um, so the reaction will finish once 1 mole of this has reacted with 2 moles of this. Now, that means that if I had 3 moles of this, it would react with 6 moles of this, because it follows the same 1 to 2 ratio. If I had 100 moles of this, it would react with 200 moles of this, and so on. That's what the benefit of this balanced equation is. It tells you a lot about the amounts that will react in that reaction. We have just worked out in this question that we reacted 45,000 grams or 236.8 moles of titanium chloride. So following the same ratio, we know that there will be twice as much of that of magnesium that will react with this. So 236.8, this is how much magnesium would react with 236.8 moles of titanium chloride. We, in this reaction, used 500 moles of magnesium. So, in other words, we've got too much. It is an excess. An excess means there's too much of it. It won't all react. We've just proved it because based on the numbers that we've got, that's how much magnesium will actually react. So 500 is too much. It is an excess. There is more than what we actually will need in this reaction. So that was that. It is again just understanding how beneficial this is to tell you the amounts of things, but understanding firstly that it's only when it's in moles that that works. Question 3 has been asked as well. All of it. Okay, I shouldn't need to do that, so I'm not going to. The percentage of calcium in that also, I don't think I need to do, but please tell me if you don't know how to do one of these. But then I can do, well, actually, I'll have to do it. To do part C, I'll have to do it. It's about reading the question very carefully. The percentage of calcium and calcium carbonate, I can tell you, is 40 out of... Oh, it's 40%. Okay, so the answer to part B, I think, is 40%. Then it says calculate the mass of calcium in each tablet, at which point you have to get to this number here from the picture, which it tells you each tablet contains 1.25 grams. And we know, because we just did it, that 40% of any tablet is calcium. So you do 40% of that. Hmm. So therefore, in that 1.25 grams, 0.5 grams is made up of calcium. 1D. Oh, sorry, yeah. Oh, yeah, that one. Okay, I'll have to read all of one first. Magnesium is in group 2 of the periodic table. 1 gram of magnesium react with chlorine produces magnesium chloride. What type of elements react with magnesium with chlorine? I think that's metal and a non-metal, because chlorine in group 7. Word equation, magnesium, chlorine, magnesium chloride. Apparatus will be a balance to represent mass. What mass of magnesium chloride was produced? Okay, so if you write this down, okay, it tells you, or we learnt in the question that we reacted 1 gram of magnesium with some chlorine and got magnesium chloride. The question is, what mass of magnesium chloride was produced? Was it less than a gram, or 1 gram, or more than a gram? Well, surely it's more than a gram, because some chlorine must have reacted with this 1 gram of magnesium. Some, right? Even if it was a tiny bit, some reacted with it, which means that this number will be more than a gram, right? Because something's been added to that 1 gram. So that's why the answer here must be more than a gram. It's just testing whether you understand that when you're reacting two things together, the overall mass has increased, right? Because of what we started with, because you're joining them together. That was 1D. Was there any other calculation in here? If not, I will move over to the other. Oh, this one. I'd like to do this. Right. Calculate. So without reading all of this crazy stuff, calculate the mass of titanium, which is there, that can be produced or extracted from 570 kilograms of titanium chloride. That's there. Again, I like to write this out. If there were any big numbers here, make sure you put them here so that you can see the ratio. This is a 1-to-1 ratio because there's one of those and one of those, which makes life a little bit easier. But the question is, if I had 570 kilograms of this stuff, how much of this stuff would I make? Now, I'm going to do this, even though you don't have to do this for this question. I would always recommend convert the kilograms to grams, because the formula for moles is mass in grams divided by mR. And I'm going to convert this to moles by dividing it by the mR of titanium chloride, which I think we did earlier, but it is 48 plus 4 times 35.5. It's 190. 570,000 divided by 190 is 300 or something, 3,000. 3,000 moles. So what we're saying is we're starting with 3,000 moles of titanium chloride. If you hadn't done the conversion there, you would have just got 3 moles over here and you'll still get it right. But I would recommend you do this. So once I know there are 3,000 moles of titanium chloride here, and I know it is a 1-to-1 ratio, it means that however many moles I've got on the left-hand side, I will get the same number of moles there. So it means I will produce 3,000 moles of titanium. But I want the answer in kilograms. So I'm going to convert it back to grams first by multiplying this, using this equation, by the mR of titanium, which is 48, to give me 144,000 grams, which in kilograms is just 144. So that's the way I would have done that question. As I said, if you hadn't done the grams, kilograms thing, you'd have still got 144. But for slightly more complicated things, I recommend doing that. And that is how you do those sort of calculations. I might just do this just to tell you what you should do here. This goes back to ionic bonding. The diagram below represents the electronic structure of an oxygen atom, which has got 2 electrons in the first shell and 1, 2, 3, 4, 5, 6 in the second shell. The question is, complete the diagram to show the electronic structure of an oxide ion. If we have an O2 minus ion, what has happened to that to become an O2 minus ion is that it must have gained 2 electrons, because that's how you become a negative ion, and you get 2 if it's a 2 negative ion, which means this now has actually got 2 more. It's got 8 in the last shell. So you need to draw 8 in the last shell. That is that. If you want to be really, really thorough and good about it, then maybe put those as a different shape to show that they have been gained from somewhere else, but you don't need to. Um, okay, that seems to be done. This was percentage yield, which I think was all easy enough, but tell me if not. Right. Anything from this? Or was it very similar? I'll do one more, just of these. Oh, there's more. No problem. Um, yeah, because it's important to get to practice these enough so that you get the hang of it. But here's another question that says, calculate the mass of nitrogen, that's there, that would be produced when 130 grams of this sodium azide, which is this thing here, there, decomposes. Right, so again, all I've done is I've taken out of the equation the bits that I care about. I don't really care about the Na in this question. We are starting with 130 grams of this stuff. And the question is, how much of the other stuff will we make? So we can't do this until we convert it to moles. So I'm going to convert that to moles by dividing by the MR of NaN3, which is 23, because that's Na, plus 3 Ns, which is 65. 130 divided by 65 is, I can do it in my head, 2 moles. Right. Well, this is nice. Because we can see that this is a 2 to 3 ratio from here, which means the fact that we've already got 2 here makes life very easy because it means that we get 3 over here, 3 moles there. Or if you want to think of the calculation, it's times 1.5, because to get from 2 to 3, we times by 1.5. We do the same thing here, but obviously it's already 2, and so it becomes 3. So that means we're producing 3 moles of nitrogen. To convert that back into grams, you times by the MR of nitrogen. Just be careful, it's N2. So it's times by 28. So 3 times 28 gives you 84 grams for the answer to that question. Mm, I think you just times your previous answer by 0.86 for this. It's telling you that 1 gram of nitrogen has this volume, but we made 84 grams of nitrogen. So times that by that. That's all you have to do there. I won't do the atom economy one. Okay. Since there's no more questions on that, I'm going to do a couple of the other questions that I did at the weekend, if I can find it. Number five, I can. This is number five, right. So, yeah, this is a weirdly niche topic, and I'm just not sure whether how often it comes up, but I'll just tell you it's quite easy to do once you do that. Essentially, the idea of this is essentially it involves converting to moles. That's the main point of this. So I'll just tell you what you do. Um, Lead oxide is made up of some lead and some oxygen. We have found that it contains 12.42 grams of lead and 1.28 grams of oxygen. Now, I am going to convert both of these to moles. So the lead I'm going to divide by 207, the oxygen I'm going to divide by 16. Okay. Now that what you have just worked out is essentially the ratio of lead to oxygen in this compound. That is the ratio, 0.06 to 0.08. So technically, this would, because remember, if I gave you, I don't know, Mg2O3, that's not a thing, but let's pretend it was. What that means is that there's two magnesiums with three oxygens. That's what it means, right? What we have just worked out is that if there's this much lead, there's this much oxygen. So in theory, this could be the formula. PB 0.06, O 0.08. But we know that we don't write these things like that, do we? We don't write decimals as the numbers that go on the bottom. No, because you'll see why the answer in your last question, you'll see why that isn't necessary. Because ultimately, what you're doing in this question is figuring out that small number. So you don't start with O2 because you are actually trying to figure out what that number actually is. Um, and you'll see what I mean in a second. Hmm. You know what? Let me just check this. Do you use a 30? I don't think you do. Because the compound is involves lead and oxygen, so I don't think you do. For this one, you don't. Because you're not converting to moles technically here. Let me just make sure that's what the mark scheme says. I'm quite confident that this is correct. No. Yeah. Yeah. So as I say, the purpose of this question is to figure out what those small numbers is. And so yes, from here, you have this ratio, but we don't like these decimals. So what you need to do is get them to whole numbers. Now, you could start off by sort of effectively timesing both by 100 and getting 6 and 8, but then you need to simplify it again and notice that both of them can be divisible by 2. And so it becomes 3 to 4 as the actual ratio. So you want this to be changed into a whole number. It's like simplifying a fraction. And if in doubt, just so you know, if you get this far in a question and you need to figure out what to do what I'm doing now, which is type those two numbers in as a fraction on your calculator, and it will simplify it to the whole number equivalent because that's what fractions do. So 3 to 4. So the actual answer to this question is it's PB304. That's what you were trying to work out. You were trying to work out what those smaller numbers actually are in this situation. Okay, let me go back to where I was. It's a very weirdly niche topic that I just don't see it ever. Um, okay, there were a couple of good questions that I did at the weekend, which I would like to bring up at this point. Like this one. Okay, right. Um, just as a little reminder about these things called moles, okay, in case you weren't explained this, like this at the weekend. Oh, there's more. One on limiting reactants. Yes, I'm about to, because there was another one to do with limiting reactants that I think I did. But I'll just do this first. Um, Remember, what the point of moles is that you are converting an amount into a specific number of particles. Because a mole is a specific number of particles. It is exactly this many particles. So if I have 1 mole of carbon, what I really mean is that I've got this many particles of carbon. That is a very big number. And that allows you to do calculations properly because we can only do it based on the number of particles. Because remember, they collide with each other to form compounds. It's about how many of them collide with each other. It's not about I've got 10 grams of this and 20 grams of that. That doesn't quite make sense in the context of number of particles because all particles have different masses. Some are heavier, some are lighter. So what they want you to do is work out in this gold ring how many gold atoms or particles there are. So I've got 3.94 grams of gold, which doesn't tell me anything. Because what I need to do is convert that to moles by dividing by the MR of gold. 3.94 divided by 197 is 0.02. So I've actually got this many moles of gold, and 1 mole has this many particles in it. So 0.02 moles has this times that many particles in it. Which is that number. Big number again, but that's how many we have got. 1.204 times 10 to the 22. That is the number of particles. Right. I'm going to find one more question if I can. The problem with limiting reactants questions is that they are not usually um, even explicitly necessary to think of it in terms of limiting reactants. Um, Partly because they will say something like, we are using an excess of something else, which means that you don't need to worry about it. But I know exactly what you mean when you talk about this stuff. So I'll do this in a different way. No. Right, this is not quite limiting reactants, but it kind of is. Okay. Hmm. It's to do with gases. So, as a quick recap of something about gases, which is, or actually, no, this is the way I want to explain this. I think this is a better way of explaining this. If I have worked out moles of a substance, which you know how to do, just to be clear, if I have moles in a question, then there are 2 ways I can go with moles. I could, well, actually, 3 ways I could go. I could work out the number of particles that I've got And I do that by timesing the number of moles by that constant 6.02 times 10 to the 23. That's what that question about the gold just asked us to do. We got to moles, and then we turned it into a number of particles. We could convert moles to grams by multiplying by the MR of the chemical that we're dealing with. So if it's 2 moles of carbon, then you times by the MR of carbon, which is 12. And so you get 24 grams. That's what another thing we could do with moles. A third thing we can do with moles is turn it into a volume in dm cubed, which is what we normally do for gases. You don't normally express gases in grams because that doesn't quite make sense if you think about it, because you can't weigh a gas in that same way. And so it is better to express gases as a volume, and that's what a question often asks you to do. To turn the number of moles of any gas into a volume, you multiply by 24, which is the volume of 1 mole of any gas at room temperature. So that makes it a bit easier actually to work with gases because you've got to remember this number 24. Whereas when it's with grams, you've got to deal with the MR. It's unique to every single substance, depending on which one you're dealing with. Whereas with gases, it's just times by 24 to get to volume. Now, I'm not sure that's relevant for this question. It isn't, but this is still technically a limiting reactants question. So just to show you, that's what we can do with moles. There's basically 3 different ways we can go. Okay. This question says that we have this substance, I don't even know what it is, silicon something, that reacts with oxygen. The equation is as shown. It tells you that 30 centimeters cubed, I'm going to write this out again, actually. It tells you that 30 centimeters cubed of this is reacted with 150 centimeters cubed of oxygen. Now, I'm going to put this in brackets because they have told you that this is an excess. In other words, there is more than this, more of this than will actually react with the 30 centimeters cubed. Come back to that. Right. It says calculate the total volume of gases present after the reaction. This is a weird question, but it's a good one to finish with. The total volume of gases present. So we know in the question that there is a gas here. There is a solid here, so that's not really relevant because it's not going to be a gas. We have a gas here, and we have a gas here. Now, when you react something with an excess of something else, then it means that all of this is going to end up getting used up. It is not. It is, in fact, the limiting reactant in this case, because the opposite of excess is limiting reactant. If something is in excess, it means there's more of it than what we need. That means the other reactant must be the limiting reactant. It's the one that's going to run out in the experiment. So now what we can do is, just like we have been doing several times in terms of all of the mass calculations, when I told you how important a balanced equation is, it is also really important now because the big numbers, the 2, the 7, the 4, and the 6, tell us the ratio of the moles and therefore the ratio of the volume of gases as well. Because remember, volume of gases is just the moles times 24, like I said to you here. So it follows the same ratio if you times all of the numbers by 24. So what I can do now is figure out exactly what volume of things will actually take part in this reaction. So if I've got 30 centimeters cubed of this, okay, that means that I've got, because it's a 2-to-4 ratio here, double the amount of silicon dioxide, so 60 centimeters cubed there. But that's not relevant because it's not a gas. Here, I've got 6 H2O, which is 3 times this number. So that means I'm going to have 3 times this volume being produced, 90 centimeters cubed. Okay, so that is definitely going to be produced. Over here now, this to this, 2 to 7, is a, well, 2 to 7 ratio means it's 3.5 times bigger, right? 3.5 times 2 is that. which means that 3.5 times this number is actually how much oxygen is going to react here, which is 3.5 times 30 is 105 centimeters cubed. That means that out of this 150, only 105 centimeters cubed is actually going to react. That's why it's in excess. I mean, I've told you it's in excess, but I've just proved it because I've just told you that we are going to only use 105 out of this 150. The rest of it is left behind, 45 centimeters cubed left or unreacted. Okay. So this is all going to finish because it's going to get used up. This is a solid, so it's irrelevant to me. This is going to be produced 90 centimeters cubed, and we're going to have 45 centimeters cubed of this left, and that is also a gas because it was oxygen. So the question said, calculate the total volume of gases present after the reaction. So in other words, what was left? We had 90 centimeters cubed made, and we had 45 centimeters cubed that we didn't use, which means the sum of these two, which is 135, is what was left at the end or present after the reaction. You don't need to convert them to moles. You can do if you like, but it won't make a difference because what if you convert them to moles, you're going to divide everything by 24 because, or in fact, even more than that, you have to convert to dm cubed first. It'll be quite complicated. You'll divide by 24, but then you're going to times it all by 24 at the end. So you will just cancel out what you did. You'll cancel out your conversion. You'll divide by 24 and then times by 24 at the end. So the only reason why that moles thing is when you're working with grams, because this is always different for every chemical, the MR, you have to do it use a convert to moles and then convert back using the MR. It doesn't follow the ratio for grams doesn't work, but it does for this because here we're just timesing everything by 24. It's a fixed number. It never changes, whereas this number changes for every chemical. Um, and so you don't have to convert it to moles. You can do, but you're going to end up doing, um, you're going to end up dividing by 24 to convert it to moles and then times by 24 afterwards. So you might as well just not done it because you're just cancelling it out. Could you do a moles question including ratios? Yes, I'll finish off with that. Um, I think I know what you mean. This will do. In all of the questions, you did moles first. Yes, but that's because we were working with grams in all of those other questions. And with grams, when you convert, like if I've got copper and copper oxide, okay, and this is, let's say, a 1 to 2 ratio, for example, and I've got 10 grams here, then this is not 20 grams just because of that 1 to 2 ratio. Because when you convert this to moles, you will get a number here. But then to convert moles back to grams, you times by the MR of copper oxide, which is different to the MR of copper. That's why you have to convert it to moles, because it's a different conversion this way than it is this way. So you can't just use the 1 to 2. I appreciate this is not a best explanation, but when you're working with grams, you have to convert to moles. But when you're dealing with volume of gases, because of the way you convert to volume, which is always by timesing by 24, no other weirdness based on the chemical, no MR that's different for everything. It will always just follow the same ratio. It's like me saying, here's a good example. If I said to you, I've got a 2 to 3 ratio, and that's 2 moles to 3 moles, and you go, okay, but let's convert it to a gas by timesing it by 24. So 48 to 3 times 24, 72. So now that's the ratio of the gases, but that's the same as this because I timed them both by the same thing. It's still 2 to 3. That's why you didn't need to do it when you're dealing with gases because you're still just that 24 is a fixed constant number for everything. But that ratio is not the same when you start realizing that if we're dealing with grams because it follows a formula based on the MR of each side, which is different. It's a different number for both of them. So that's why you have to do that. Right, last one I'll do, which is this. Isn't 1 gram equal? I don't know what that means. 1 gram doesn't equal 1 centimeters cubed. 1 gram is a unit of mass, and centimeters cubed is a unit of volume. So no. Um, yeah, but as in grams are a different. The grams are a measurement of how heavy something is. Centimeters cubed is a measurement of volume. They're two different things entirely. Um, right, last one of these. The equation for the reaction between nitrogen and hydrogen to produce ammonia is as follows. Calculate the mass of hydrogen, which is there, needed to produce 25 grams of ammonia, which is there. So just to be clear, in answer to the other questions, we are dealing with grams in this question. Therefore, I am going to convert to moles to figure this out. Okay, so NH3, the question is 25 grams of this. Right. So what I need to do is convert this to moles, because just to be clear, whilst this is a 3:2 ratio, this is not a 3:2 ratio in terms of grams. It is a 3:2 ratio in terms of moles. So divide by the MR of NH3, which is 14 plus 3, which is 17. 25 divided by 17 is 1.5. Let's call it now 1.47. Okay, right then. So that's the number of moles that I'm producing. The question is, how many moles of this will I need? Well, the ratio tells me that it's a 3:2 ratio or 2:3 ratio if we're going this way, right? So the way I would do this is to go, how do I get from 2 to 3 by multiplying? I multiply by 1.5. Or you could divide by 2 times by 3. It's the same thing. But times by 1.5 gets us from that side to that side, which is 2.2 from memory. 2.2. So we have got 2.2 moles of hydrogen. Now, just to be clear, there are two ways that I could go here, depending on the question. Again, it's important to be adaptable. If the question had said, what is the volume of hydrogen gas produced? I would times this by 24, because that would turn moles into a volume. The question is not what volume of hydrogen gas was produced, it says what mass of hydrogen was produced. So now we turn this back into grams by multiplying by the MR of H2. The MR of H2 is 2, which gives me 4.4 grams of hydrogen. So just to be clear, in grams, that is 4.4. In volume terms, that is 52.8 dm cubed. So I suppose that proves the point, which is 1 centimeters cubed is not the same as 1 gram, because it's just a different thing. So if this question, yes, good point. If this question had said, right, let me do this to finish. So that's the answer to that particular question. Right, let me get rid of all of this. If this question, if I change this question completely and say that I began this with 25 centimeters cubed of ammonia, how much of, or I finished with 25 centimeters, how much hydrogen did I start with? Let's say that was the question. Hopefully this will work. I don't like making up these calculations. But let's do this the long way. And, I'm going to change to dm cubed because that's the unit that we normally use for volume. Okay. If I said, right, let's do this using the whole moles process. To convert volume to moles, you divide by 24. So 25 divided by 24 turns that into moles, which is 1.041. Okay, then I will use the balanced equation to see that's a 2 to 3 ratio. So to get from here to here, you times by 1.5 like I did before, which gives me 1.5625 moles. Okay, and then to convert this back to a gas, to convert moles back to a volume, you times by 24. And I get 37.5 dm cubed. So that works. That is the answer to the question. But I didn't have to do the whole mole conversion there because I could have just followed the ratio at the beginning. Because 25 times 1.5 is 37.5. So do you see what I mean? We can comfortably do that. That's fine. But because you divide by 24 here and then times by 24 here, you're effectively cancelling out that process. You're dividing by a number, then timesing by a number. So the whole process is is cancelled. You're just basically following the ratio of 2 to 3 there. That doesn't work with grams because you don't divide by the same number here that you times by over here because the MR of the two different things is different. Hopefully that answers those questions. It is 9 o'clock. Um, so yes, we are doing a bit more electromagnetism next week. And also, just so you know, for those of you in year 11, we are doing waves with the year 10 students, which means that next week I will do some waves stuff. All of this is relevant for you because you have exams in less than 6 months. So all of those topics are still relevant, whilst we might not do it in the lessons until the end. If you come to these sessions, you will still do a little bit of recap of things like electromagnetic waves and stuff, because we will be doing some of it next week. Right, I think that's it. I'll let you, or I'll go, and I'll see you next time.